Hello everyone, and welcome to the PCD of Codeforces Round 1033. Before we start, am I audible? Also, how was the contest, guys? Like, a lot of people are pretty annoyed about this contest, I think, right? Like, especially the first few questions weren't that great. Am I audible, guys? Can you post in the chat if I'm audible? Just confirm and then we'll start. We'll discuss A, B, C, D, E. System testing is still going on. Yep, okay. How was the contest, guys? Yeah, we'll get to B soon, clumsy man. And then, like, we'll discuss all from A to E. And after that, we'll even have some general talks if you want. Okay, so before we get started, I'd like to tell you that if you haven't checked it out before, do check out the TL Eliminators self-paced courses. They are live now. In fact, there's a sale going on right now, so they're at a discount. And the way our courses is done is that it's divided into 4 different levels based on, which like current rating you are, which topics you need to learn. So you can go see the topics, right? And you can see which level is suitable for you, right? And you can get started with it. It's the main, reason for taking one of these courses is because it's very organized, right? If you just do learning by yourself on the internet, sometimes you get confused that, what should I do next? Here, there is no doubt in your mind what you should do next because everything in the course is organized. There's 40 plus hour of recorded lectures. There's 100 plus practice problems. Then if you ever get stuck, you watch the hints, the video solutions, and there is non-stop doubt support available by high-rated coders, where even I do doubt support, right? And then in the end, there's even a leaderboard to gamify the whole process and help you um, be motivated to, achieve more. Okay. Problems are weird. Yeah, slightly weird because at least A felt weird to me. Like I spent half an hour on A, and like for me, for a person like me to spend half an hour on A, like, that's very um there was definitely like a lot of casework in A. I don't know. A lot of my friends also found it a bit weird. Okay, so let's jump right into it. What does the question A say? Um, Square of rectangles. Aryan is an ardent lover of squares, but a hater of rectangles. Okay, but Harshit likes to mess with Aryan. Harshit gives Aryan 3 rectangles of size L1 into B1, L2 into B2, L3 into B3. Okay, such that L3 less than equal to L2 less than equal to L1 and B3 less than equal to B2 less than equal to B1. Okay. Aryan, in order to defeat Harshit, decides to arrange these 3 rectangles to form a square such that no 2 rectangles overlap and the rectangles are aligned along the edges. So rotating rectangles is not allowed. Okay, this is a very key point. Rotating rectangles is not allowed. Help Aryan determine if he can defeat Harshit. Okay, so basically we need to see if we can take these 3 rectangles which are given to us, right? So we have some 3 rectangles. Right. One sec. Yeah. So we have 3 rectangles given to us, right? And they have some length and breadth each. Okay. So this is rectangle 1, it has some length and breadth. Rectangle 2, it has some length and breadth. And rectangle 3, it has some length and breadth. So this is L1, this is B1. Or sorry, length should be along this side. So L1, B1, L2, B2, L3, B3. Right. And we need to see if there is some way to stack them so that they can form a perfect square, right? So then, well, how do you approach this problem, right? So I just want to inform you, like when I was solving the problem, I did not notice that this part, like usually when you're solving A, right, you're in a bit of a hurry, especially if you're a high-rated contestant. So I did not notice the line which says L3 is less than equal to L2 less than equal to L1, and B3 is less than equal to B2 less than equal to B1. So that's why in my code, if you see, I wrote down many cases, but actually there were only 4 cases to consider. But yeah, let's go through all the cases. So yeah, so here in this example, this should be L3, right? Because L3 must be smaller than all the others. So this example was just to show like 3 rectangles, that's all. So what is our case one? Case one. So there are basically 4 cases which happen, right? And how do you get these 4 cases? You get it with some tinkering and some, trying some stuff out. So the first case is that we have, okay. So first thing you should know is that if we have them to form a square, right? Then let's say the square has a side of S, right? Then the total area should be equal to S square, right? So what I did was in the very start, I found the total area. So that is L1 times B1 plus, so let's call this area equals L1 times B1, L2 times B2 plus L3 times B3. So this is obvious. We just take the total area. Then we set S equals square root of this total area, right? So this is the length of our side. So we can get that if they have to form a square, it must be of exactly side S, right? Because that has the same area as all these 4 shapes, since they can't overlap or anything like that, right? And also if this is not an integer, so if this is not integer, then obviously we can print no, since their total area is not forming a square, right? Print no. Okay. So now assuming that the area was a square and we found the value of S, we found the value of side. Now we are going to do the remaining steps. So then in that case, so first we have this case. Here L1 plus L2 plus L3 equals S, right? In this case, L1 plus L2 plus L3 equals S, and B1 equals to B2 equals to B3 equals to S. So this is the first case. Okay. Now what is the second case? And basically this problem is all about just making the cases and solving it. I have seen it reduced to 4 cases because we have that L1 is greater than equal to L2 greater than equal to L3. But yeah, I think that you can't have less than 4 cases. There are 4 cases for this question. And then the other way we can do it is we can have something like this. So let's say this was L1, and then we have something like this. This is B1, B2, B3, and this is L2, L3. So we stacked all of them like this. Basically, we're stacking them vertically, or you could say like L1, B1, then L2, B2, and L3, B3, right? And this can form a square, right? And for this, the condition will be L1 equals L2 equals L3, and B1 plus B2 plus B3 equals S. Okay, so this is the condition in second case. Now let's quickly find the other 2 cases in which this is possible. In one of the other cases, we can have something like this. So this is L1, this is L2, this is L3, and we have something like B1, B2, B3. Okay, so roughly something like this, right? So this case can be written as L1 equals L2 and L3 plus L1, L3 plus L1 equals side, one side. B1 plus B2 equals side equals B3, right? So this is our third case. And our fourth case is the same, but like vertically, if we do the same thing. So it's like we have 1 over here, and then we can have 2 like this, right? So this is our L1, this is L2, this is L3, right? And yeah, okay. And also here, if you observe, the longest side must be B1, right? So since the longest side must be B1, we can write it something like this. We can write B1 over here, we can write L1 over here, and we can write L3 over here. Okay. Now in this case also, longest side is L1. This is B1, B2, and B3. So we can write this case as L1 equals S equals L2 plus L3, and B1 plus B2 equals S, B2 equals B3, right? So then these are the four cases which are formed, and you just need to check if first you need to find the area, right? Then you need to find the length of the side. Then you need to check if all these four cases are possible, and if any one case is possible, you can print out yes. Otherwise, you can print out no. If you observe, there's no other way to stack it so that it forms a square, right? These are the only four ways you can stack to form a square. That makes sense? Yeah, A was pretty hard, I think. Like, I don't know, like I was thinking if there's more than four cases, and then I didn't notice that L1 is greater than L2, greater than L3. So what I ended up doing was I wrote a lot of cases actually. Like I didn't notice L1 greater than L2 greater than L3. So I wrote like a bunch of cases. Like if that is not true, right? If L1 greater than L2 greater than L3 is not true, then what happens is that here instead of L1 and L3 exactly, because we know that B1 is largest, so we know that B1 is the one going at the bottom, right? But if that was not true, we could try B2 here, then we could try B3 here. So this would form three cases, and this would also form three cases, right? If that was the case. So that's why my code is a bit ugly, you could say. Like this is the first case, and this is the second case. And the third case is that so the largest side, B1 plus B2, should be equal to B3, right? So it should be something like this. B3 plus B2 equals B1, right? So here B1 equals to S should be the correct one. Where is that? Uh, Here we have L1 plus L2 equals side. And yeah. So yeah, these two cases are actually not required. Like this one is not required. And this one is not required. So yeah, these are the four cases which are actually required. But during the contest, I was in a hurry, so I did not think that much. And I did not read the question properly. So yeah, that's it. These are the four cases, and this is the final code. Right? Here I did an additional check just to make sure that the largest one doesn't become bigger than a side, but that is also not required for the answer actually. So yeah, this is the final code. My original code was also correct, that the code will be linked in the YouTube section, but it's just too long. You can see this code. It's based on this logic, right? So just basically like find the area, find the side, write all the four cases and test all the four cases one by one, and then print yes or no. Does that make sense, guys? Should I move on to the next question? Right? You can just quickly run this and see if the cases I removed were the correct ones. Yep. Should I move on to the next question or any doubts, guys? Compare L1 and B1 to find max. Why would you do that? Yeah, you can do that also, but you can directly just check these four cases as well. Okay, should we move on to question B? Any doubts? Or otherwise, within 1 minute, we'll move on to B. Okay. Let's discuss question B. Square pool. Okay, so this question, I think some intuition is required. Like if you have done physics problems before, I think it would be easy because you need some physics intuition, right? Otherwise, like, or if you're good at guessing from the test cases, otherwise, I think it was like it looks very difficult in the start. Aryan and Harshit are playing, so all this is not very required, but they're playing on a square pool table of side S. Okay, so they're playing on a pool table, which is a square of side S, and it has pockets at the four corners. Okay, and the corners are situated at 0, 0, 0S, S0, and SS. Okay, so you can imagine like a coordinate plane, and then in that we have four corners 0, 0, 0S, S0, and SS. In this game variation, n identical balls are placed on the table with integer coordinates such that no ball lies on the edge or the corner of the table. Then they are all simultaneously shot at 10 to the 100 units per second speed. So that means at very, very high speed they're shot. Okay? That's basically what it means. Almost infinite speed they're shot. Only at 45 degrees with the axis. Here the balls and pockets are point-sized. Collisions are perfectly elastic. Okay? So there's like perfectly elastic collisions as well. And then on hitting any surface, it will bounce off with the same angle and the same speed. Okay? So that makes sense? Right. Harshit has shot the balls and he provided Aryan with the ball's positions and angles which he shot from. Help Aryan determine the number of balls that have been shot collisions don't occur at any time. Okay. So there are three test cases and each test has two integers n and s. So this is the number of balls and the side of the square pool table. Then each test case contains of n lines, which has dx dy, which means direction of vector for that current ball and position x and y of that current ball. So the direction vector, we know it is 45 degrees, right? So let us draw the question to understand what's going on. So we have a table like this, right? And let's say this is our 0, 0. This is our 0s. This is our s0. And this is our ss. And then we have some bunch of balls here, which are like points, almost point sized, right? And then we're given the coordinates of the balls. And we're also given at what direction they were hit. And we know that it's a 45-degree direction. So either it's going to be like, and the way it is given is +1 means it's going towards up, right? On this axis. And here also +1 means this. So it's like vectors, if you have studied vectors, you know, they're just telling which direction the ball is going, right? So these are the direction vectors. So 1 unit or 1 unit in this direction, 1 unit in this direction, that's the angle which is given, right? And it is also guaranteed that sum of n does not exceed 10 to the power 3. I don't know why that was required for this question, to be honest, but yeah. Okay. So let us see a diagram to understand what's going on, okay? So in the start, if you look at this diagram, the balls are at these positions and they're given some direction vectors, right? And then they start moving towards this direction, like this ball moves towards the, you could say, top left. This ball moves towards bottom right. This ball moves towards bottom right. And they're doing perfectly elastic collisions. So if you have an idea of how physics works, perfectly elastic simply means when two balls collide, they will basically uh, exchange the kinetic energy perfectly. And then when one ball hits the wall, it will get reflected along the axis, which is perpendicular to the wall. Like the kinetic energy remains the same, it gets reflected in that way. So basically what it means is like if a ball hits like this, it's going to bounce like this and go off, right? So if a ball is coming to the wall, let's say a ball comes to the wall, it's going to bounce perfectly and go off, right? And then if two balls hit each other, like there's a ball here and a ball here, they're going to perfectly go back like this, okay? So like they're going front and facing each other, and then they'll go back and still face each other like this, right? So that's all perfectly elastic means for this question. So we're given these balls, and we can see that, okay, there's some collisions occurring and stuff happens, right? And then the most interesting part is Like here we see that these two balls collided, so now they're going in opposite directions. Then these two balls collided, they're going in opposite directions. Here there's a very interesting thing. Observe that this purple colored ball, right, which is moving towards the black colored ball. So when it is along this diagonal, if you observe this purple colored ball hits the black colored ball here, and then what happens is when they're at the same position, their vectors get switched, right? Their vectors are getting switched. The purple ball has taken the place of the black color ball, and the black color ball has taken the place of purple color ball. But there's still two balls moving in the same directions itself. Just because of perfectly elastic collision, the vectors became switched over here. So that's what happens when two balls collide in this setup, right? So in the end, we can see that two balls keep remaining going around infinitely, and the remaining balls reach the pots. So how do we solve this question? Right. So how do we solve this question? If we look at the diagonal, right? So we know that the pots are towards the diagonals itself, right? So look at the diagonals, and you can observe that if there is a ball moving along the diagonal like this, so obviously it's going to get into the pot. But what if some ball was in the way? Let me just remove some stuff from the diagram so that it looks clear, okay? Let me just wipe all these extra dots. Okay. So let's say there was one along the diagonal and one along the diagonal. And we'll see that the diagonal is very special to the solution. Okay? We'll see that the diagonal is very special to the solution. Okay. So if we have a ball coming like this and coming like this, what happens is they'll hit the midpoint and they'll reflect back, right? So both of them still end up reaching the pot. And what if some ball from outside comes and hits one of these balls? Well, we saw in the example itself what happens. Like even if you do not know the physics, you can see that in the example itself, when two balls hit each other and it's a perfectly elastic collision, they swap places. Like the purple ball, which was going front, now the black ball is going front and the purple ball is going down, right? Can you observe that? Right. So if we have a ball which comes like this, so there's a ball which is going, let's say upwards. Let's say there's a ball going top left along this diagonal, and then it hits a ball which is going like this. Then what happens is this original ball starts going this way and the other ball starts going this way, right? So there are still two balls itself. There's still two balls itself going like this, but they've become swapped. So this ball becomes this way and this ball goes this way, right? So the ball which was going like this starts going like this, and the ball which is going like this starts going like this. So essentially nothing has changed. The balls have simply swapped. So from this, what we can conclude is that all the balls which are along the diagonal initially, right? All the balls which are along the diagonal initially, like that many number of balls itself will reach the pot. Okay. The number of balls which were along one of the diagonals initially, that many balls itself will reach the pot, and no other balls are going to reach the pot. Why is that so? Because like it's not that the balls of the diagonal are going to reach the pot, they might get changed, but the number of balls which are on the diagonals, those are the ones going to reach the pot. Because if they're on the diagonal and they have no interference from outside, they're going to go directly into the pot, right? So this is our key intuition, is that only diagonals are important, because first of all, we know that they're in 45 degree, correct? So first of all, we know that the balls are in 45 degree. So the only way you can reach one of these points is if you were along this diagonal and you're hitting that. There's no other way to reach these points, right? So then it must be a ball along this line, right? And all the balls along this diagonal are going to reach one of the pots. If some external ball hits them, then the two balls get swapped, right? So even though the two balls get swapped, the number of balls along the diagonal remains constant. And in the end, all the balls along the diagonal, they go inside, and the remaining balls keep moving around. So the answer, like, I guess it takes some physics intuition. Like for me, this was a pretty quick answer. but I can see why a lot of people struggle with this. The answer is simply number of balls along the diagonals. Moving along diagonals. Okay. And that's the key intuition. And let's just reiterate why why I said this is because all of the balls are moving at 45 degrees. That means to reach this point, you must be moving along the diagonal. And if you are moving along the diagonal, well, initially either you were moving along the diagonal or you swapped with something which was on the diagonal. So the number of balls along the diagonal remains a invariant, right? Number of balls along the diagonal is invariant. And eventually, if you're moving along the diagonal, you will reach one of the pods. Is invariant, right? So these are our two intuitions. And I can't say, yeah, this is harder than usual B, I think. Like they should have put this for C, maybe. I'm not very sure. But again, they're just testing geometry. Like A also tested some geometry, and I did not enjoy A. B is testing like physics plus geometry. So since I had done like some brain teasers and stuff for physics prior, the knowledge, the intuition came quickly for me, I guess. So how do we check if a ball is on diagonal? Well, we can say that the first diagonal is from 0, 0 to SS, right? So to just check this diagonal, all you need to do is check if it's 1, 1, 2, 2, so on, right? So if X equal to Y, and also we need to make sure that it's going along this diagonal, right? So this should be +1 and this should be +1, or this should be -1, and then this should also be -1. So if X equal to Y and D1 equal to D2, then we can say that this is along a diagonal. So we can increase our count. Similarly, if we can have, so what about this diagonal 0S and S0? If you observe here, this becomes S minus 1, 1, then S minus 2, 2. So the equation for this line will be X plus Y equal to S. And along this diagonal, the D1 and D2 values will be different. So if we want to move along this, either this should be -1 and this should be +1, or the other unit vector should be -1 and the other vector should be +1. So for this diagonal, to move along this diagonal, the condition is D1 not equal to D2, right? So in this both cases, we'll do count plus plus, and finally we'll print the final value of count. So that's all. The code for this problem is actually pretty short. So we have our initial count variable equal to 0. Then from I equals 0 to n, we'll take directions x and y as input. If it's along the first diagonal, right? If it's along this diagonal and its direction is correct, like it's moving along the diagonal d1 equal to d2, because if you're moving along the diagonal, if you're moving along this diagonal, your angle should be 45 degrees exactly. So this should be 1 and this should be 1, right? Otherwise, this should be -1 or this should be -1, and you're moving along this diagonal. So that's why we have d1 equal to d2. Then I increase my count. Otherwise, for the second diagonal, you can see the equation of the line is x plus y equals s, right? Just simply observe. The first one is s0. Then the next one is s minus 1, 1, s minus 2, 2. So simple maths. This line is x plus y equals s. And we can see that to move along this direction, your d1 should not be equal to d2. So either this should be like +1 and this should be -1, or this should be -1 and this should be +1. All right. So that's all for B. Any doubts? B language was complex. Yeah, to be honest, B the language was a bit complex. Please tell us about the art of guessing from sample cases. Well, we can discuss that at the end. But yeah, that only happens. Usually that happens with practice. Like I did not enjoy the contest today. To be honest, in the start, I also did not enjoy the contest. A, B were not that great. And after C was hard. After C was okay, I think. Yeah. Okay. Debashish says you cannot understand, so I'll just explain once again very briefly. Okay. Assume this is our pool, like this is our table, and then these are the 4 points which are valid. Okay. So these are the 4 points which are valid exits. Like when we, what is that called? Pockets, right? So when we hit a ball, it should go to one of these four pockets, correct? So it should go to one of these four pockets, correct? Now, I have a bunch of balls, and let me do that in green, okay? So let's say I have these four balls, okay? And let me give them some directions as well. So let's say this is going along this direction. This is going along this direction. This is going along this direction. And here this is going along this direction, right? And the direction is given by that vector. So this means 1 and 1. This means minus 1 and this means 1. This again means 1 and 1. And this means minus 1, minus 1, right? So we know the ball's positions, we know the directions, right? Now we need to see how many balls can go into the pocket, correct? So when we observe all the balls are at 45 degrees, we can observe that all balls are at 45 degrees. So the ball must be moving along this diagonal, this 45-degree diagonal, to get into this pocket, right? So the ball must be moving along the diagonal to get into the pocket, the pink color diagonal which I just drew. So the ball must be moving along diagonal, to get into the pocket, otherwise it will never get into the pocket, right? So let us see if we just need to count all the balls in the diagonal, or some balls can escape, or some new balls can join the diagonal, right? And there are two diagonals, obviously. Like one is that first pink diagonal, and then is the orange diagonal. And any ball along these diagonal is currently moving towards the pocket, right? So if there was a ball over here, and it was moving like this, then it would also be moving towards the pocket. Okay. So for now, I'll just draw one diagonal, not to confuse. Okay. So now let's say there was another ball over here on this diagonal itself, and it's moving like this. Okay. So what happens to these two balls? When they collide, they'll collide at this point, and then they'll start going backwards because it's a perfectly elastic collision. So their kinetic energy just gets switched and they'll start going backwards. So the number of ball does not change. So we can say that during an internal collision, during collision of two balls in diagonal, number of balls along the diagonal does not change. Doesn't change. Okay. We can call this, so this is two balls inside the diagonal. Okay. Now what if one ball from outside the diagonal comes and hits a ball inside our diagonal? Okay. So I'll draw that case as well. So assume that this is some diagonal which we have over here. Okay. So this is our diagonal. I drew a dotted line. Okay. And our ball is the one in green. It's going like this, right? And there's another ball which is coming like this, right? And when they collide, they'll collide at, let's say, this position, right? They'll collide. What happens is this ball starts going this direction, right? Their kinetic energy swaps. That's what happens in perfectly elastic collision. So this ball, so let's call this ball one and ball two, okay? So this is ball one, this is ball two, right? And they're both coming and hitting this point on the diagonal. Then what happens afterwards is ball one starts moving with the kinetic energy of ball two. So ball one moves in this direction and ball two moves in this direction. So what we can say is one ball has left the diagonal, one ball, which is ball one, left the diagonal, but one new ball joined the diagonal in its place, right? One new ball, ball two, joined the diagonal, right? Joined the diagonal. So again, there is no change in number of balls along the diagonal, right? So again, we can say no change in number of balls along the diagonal, right? So if you observe in the test case also, they gave an example where they depicted this happening. These two balls, one is going along diagonal and one is not going along diagonal. They come here, the kinetic energy gets swapped, and then they keep going onwards. right? So from this, we can say that since nothing is changing the number of balls along the diagonal, and only the balls along the diagonal are going into pockets, our answer will be simply counting the balls along the diagonal. So our answer will be count the balls along the diagonal, and those are the balls which reach the pocket, right? Balls along the two diagonals. Okay, right? So is there still a doubt, or is my idea clear? Let's see. Debashish, do you understand this? I think someone else is doing today's lead code contest, but I'm not 100% sure about that. Focused. Look at the downwards. Yeah, there is. I can agree. A and B were not that nice. Like B's language was very unclear, and especially if you don't know much physics, it would be hard. And A, I just did not like. Like I also took 30 minutes just to think through all the cases. Yeah, unfortunately, there is some cheating these days. A lot of cheating, I think. We can't do anything about that. All right. Yeah. Okay, should we move on to the next question? So now we simply need to count along the diagonals. We can check the formula for the diagonals. So these are the two formulas which I discussed for the diagonals, right? X equal to y is the first diagonal, like this. And the direction should be either 1, 1 or zeros or minus 1, minus 1. And x plus y equals s is the second diagonal. And here direction should be either minus 1 plus 1 or plus 1 minus 1 to move along the diagonal. And so you finally get this code. Okay, any more doubts on B, and we'll go to C. Okay, let's start the discussion for 3. System testing not over yet. Okay, system testing is over. Fine. Harshit attained enlightenment in competitive programming by training under a divine tree. A divine tree is simply a rooted tree with n nodes. Okay. The divineness of a node is the smallest label on the unique path from the root to V. Okay. So basically, we're in problem C now. What is the question saying? We have a tree, a divine tree, and the divine tree has n nodes, and the n nodes have a label, unique label, which is from 1 to n. Okay. So basically, some node is labeled 1, let's say, and then all the other nodes are labeled something. Like everyone has a label from 1 to n, like 1, 2, 3, 4, 5. If there are 5 nodes, each node will have some label or the other. That's what this says. Then the divineness of a node is defined as the smallest label on unique simple path from root to the node V. So if we choose node 2, then its divineness will be the smallest node on this path. Let's say this was the root, right? So the smallest node on this path is simply 1. And so the divineness will be 1. And in fact, all the nodes will have divineness 1 since the root is very small. But let's say we change the root. Let's say the root was 5 here instead. Let's say the root was 5 here. Okay. Now, let's say we pick this node. What is the divineness? So we see that the path from root to this node is 5, 3, 4. And the minimum of 5, 3, 4 is 3. So that is the divineness at this node, right? Similarly, we can write divineness of the other nodes. We can write here 5, 1, 2. So these are the divineness of this example tree. Okay, so we understood what divineness of a tree means. Now, Aryan, being a hungry competitive programmer, asked Harshit to pass on the knowledge. Harshit gave him this condition that he would be given two positive integers n and m, and you have to construct a divine tree with n nodes such that the total divineness sums to m. If no such tree exists, report that it is impossible. Okay, so basically, this is the definition of divine tree, right? So this is what a divine tree is, and our task is um, find divine tree, with n nodes, such that the sum of the divineness, right? So sum of divineness values for all nodes, that is equal to m. So basically these divineness values which we calculated in pink color over here, they should sum to m, right? So that is the problem statement. Let us see how to approach this. Navneet Singh, well, if you're having trouble understanding, then you can tell me what exactly you're getting confused on, or when I make a statement which you get confused on, you can tell me, okay, this statement I didn't understand. So I'll try to explain that again. Most tier 3 students don't go up to master above because it's only for tier 1 students. Look, I myself am not from a tier 1 college, right? So there should not be any bias like that. Tier 1, tier 2, tier 3 does not matter that much. It just means how good you are for physics, maths, and stuff like that, right? Because that's what you were tested on. So you shouldn't think like that. Okay, back to the question. How do we make a divine tree which has n nodes and which has a sum of m? Okay, so first I want to find out. So here's the way I'm going to approach the problem. How to make tree with n nodes and sum of divineness m. Also, if it's not possible, we have to print -1s that was given in the question, right? And also let us, now that we're on C, let us check the time complexities as well. Here n goes to 10 to the power 6, m goes to 10 to the power 12. So roughly we want a big O of n-ish solution, right? Or n log n also might work, but since they wrote 10 to the power 6, it might mean they want big O of n solution, right? Okay. How to make a tree with n nodes and the sum of diviners should be m. So first let us find out. Let us constrain the problem, okay? Constrain the problem by finding what cases are impossible, okay? Like, what is the minimum divineness we can make? What is minimum divineness we can make? Okay. And then we can also check what is maximum divineness we can make. For any tree, right? So let us try to answer these two questions and let us see. So let's say we have n equals 4 nodes. Okay. What is the minimum divineness we can make? Well, we can make some tree like this, right? And if we put our first value as 1, okay, so our first value is 1, then if we write 2, 3, 4 here, since this is our root, right, so we made our node 1 as the root, then the divineness over here, here, and here all will become 1, right? Because along the path from 1 to 3, or along the path from 1 to 4, or along the path from 1 to 2, there is a value of 1 occurring, which is the smallest value. So the minimum divineness, min divineness, we can construct. Okay. Now, what if we had to make max divineness, right? So again, for n equals 4 node, we will try to make max divineness. Here, let us make 4 our root node. Okay. And then we will have 3, 2, 1. Okay. And here, what will be the divineness? Well, for 4, it will simply be 4 itself. Similarly, for 3, this is the path from root, right? So 4 is our root node. This is the path from root, so it will be 3 itself. Similarly, here it will be 2 itself. Here it will be 1 itself. So the divineness equals 4 plus 2 plus 3 plus 1, which is n times n plus 1 by 2. And this is our maximum divineness. Okay. Oh, sorry, the minimum divineness constructible should be n because we have 1 into n, right? So 1 into n equals n. So we can say that our divineness value or m. So m is the required divineness, right? So if m should be less than equal to n and should be less than equal to n times n plus 1 by 2, right? Otherwise, we can simply print minus 1. Otherwise, not possible. Okay. So is this much clear, guys? The divineness should be between these two. No, minimum divineness is not n minus 1. Minimum divineness will be n. Because for each node, we're summing the divineness. And for each node, the minimum can be 1. So the total minimum will be n. Okay. I know I have not changed my ID. I have not changed my ID, guys. My ID is the same. Yeah. Okay. So let's move on. Let us try to construct. Okay, so we saw how to construct exactly n. We saw how to construct exactly n times n plus 1 by 2. Let us try to construct the numbers in between and check if all of them are possible or not. Okay. So for n times n plus 1 by 2, so let's say this is our node 1, this is our node 2, this is our node 3, this is our node 4. And let's say we have 5 nodes total. Okay. And we want to construct a target 13. Okay. So what I can do is any number, my observation basically is, my observation is like the node 5, right? Divineness of a node is equal to the value at that node or any number lesser, right? I can make it equal to any number lesser by connecting it to the correct node. So for example, if I have node 5, right? So if I have node 5, if I make it the root itself, then the divineness will be 5, correct? But if I connect it to 4, then this one's divineness also becomes 4, right? So by connecting the larger one to the smaller one, I have given the smaller, like the larger one, the value of the smaller one, right? So here divineness becomes 4, 4, right? Similarly, if I connect 5 to 2, right? If I make 5 the child of 2, then I can directly give it the value 2 because that is the smallest thing which is coming till the root, right? So basically, once I choose my root, right? Any other number, I can give any value less than equal to the current node, okay? So basically, I can choose my tree in such a way, and this is the key intuition. I can choose to connect my node in such a way that its divineness becomes any value less than or equal to it. Okay. So basically, I can choose to connect that node in such a way that a divineness value becomes less than or equal to it. Let us see with this example. So here I'll give an example. I have these nodes 1, 2, 3, 4, 5. And what sum I want to make, let's say the m I want to make is 11. Okay. So I want to make the sum 11. Let us see how I can make the sum 11. So let's say if I write 1 plus 2 plus 3, so that's 6, right? Plus 4, and then I have 1 left over. Okay. So if I write 11, I can write it like this, right? It is equal to 1 plus 2 plus 3 plus 4 plus 1, which is left over. So simply what I need to do is, for this much part, I want all the values to stay the same. And then for the remaining part, I want the value to become 1, right? So I can make 4 as my root node. Okay, 4 becomes my root node. 1, 2, and 3 are connected here, right? And the fifth one will be connected here. So then if you observe the divineness values, it will be 4, 1, 2, 3, and the divineness value for this also will be 1. So I have achieved my target, and this is a valid tree. Okay. Now what if instead of m equals 11, it was m equals 12? Okay. So what if it was m equals 12? So here I can write 12 as 1 plus 2 plus 3 plus 4 plus 2. Right. So I want 5 to become equal to 2. So basically I'll draw a connection from 5 to 2 in my final graph. Right. So here I can write it as like this. Right. So the divineness value at 5 becomes 2. And my final sum will become 1 plus 2 plus 3 plus 4 plus 2 equals 12 as I require. Yeah, Jiang Li does write the readable code usually. Yeah. Boombox, that's correct. If m less than n and m greater than n times n plus 1 by 2, return answer. Yeah. So basically what I'm doing is for any target, I can reduce my last few nodes, right, as much as I want to become equal to that target. Like, how do I say this clearly? So basically I can reduce. So this is going to be my idea. I can reduce the divinity of last nodes, the divinity of last few nodes until I get my desired m, right? I get my desired m. Okay. So basically, in the start, I have all my nodes as different values. All my nodes are 1, 2, 3, 4, 5, let's say. My m is now 3. Okay. So my m is 3. So what I'll do here, instead of 5, I'll connect this to 1, right? So now this one will have a divinity of 1, correct? I'll connect this to 1, and now this one has divinity of 1. And what happens? How much I need to remove? So basically, we need to remove this much value. So this is the sum from 1 plus 2 plus 3 plus 4 plus 5. How much is that? That is 5 times 6, so 5 times 3, 15 minus 3, right? So we need to remove 12 total. By doing this connection, I have removed 4 from the divinity, right? So initially my graph, I'm assuming all the values are equal to their values. So initially I have a graph like this, right? So initially I have a graph like this, and then the total sum will be 15. Then I can remove 3 by connecting 5 to 1 instead. So my graph becomes something like this. 3, 4, and then 5 will be connected to 1. So if I make my graph like this, now the value will become 12, correct? So now I need to still remove 12. So what I can do is, um, I will connect 4 to 1 again, right? And that will remove another, so how much did I remove? Now I need to remove 8 more, right? So from 12, I removed 4. So I need to remove 8 more over here. Then I connect here, and the value of divinity goes from 4 to 1, right? If I make a connection from 4 to 1, again, my value of divinity goes to 4 from 4 to 1. So 8 becomes 8 minus 3, which becomes 5, right? Here again, I need to remove 5. So if I connect from 3 to 1, it becomes 5 minus 2, which is 3, and so on. Also m can't equal to 3 because obviously it's less than n, right? Sorry about that. So let's say m was equal to 5, which is our smallest case, right? So now let's just recalculate these. If m was equal to 5, then the first connection, so we start at 10, right? So the first connection removes 4. So now we need to remove 6 more. Then the second connection removes 3. Now we need to remove how much more? Now we need to remove 3 more. The third connection removes 2. Now we need to remove 1 more. So we'll make this final connection to 1. And so what the final graph we get is something like this, which we expect 1, 2, 3, 4, 5, right? Yeah, sorry about that, Dhanyajay. And m equals 3 is not possible for this setup. That's correct. So I took m equals 5. Let's do one or two more examples just to make sure that we understand what's going on. So let's say m equals 8. Okay. M equals 8, and we have again 5 nodes, right? Again, we have 5 nodes. Now, how much is the remaining? The remaining is 5 times 6 by 2 minus 8. So this is how much we need to remove from the completed graph, like the graph which has maximum. So we can say that this is 15 minus 8 or 7, right? So first we'll connect from 5 to 1, and we can remove 4 from 7. So 7 minus 4, and we get 3. Now we can remove 3 from 4, right? We can remove 3 from 4 by connecting it to 1. So this one becomes 1, this one becomes 1, and these remain 1, 2, 3, right? So these remain 1, 2, 3. So our final graph looks something like this. Will this contest be unrated? I'm not sure. It might actually be. Like, it was pretty severely disliked. So yeah, this is the tree we get. So let me just clarify the idea, okay? Our idea, any value m between n to n times n plus 1 by 2 is possible. Initially, we maintain an array. Initially, their divinity values for maximum case, we'll have an array for that, okay? So we'll have their divinity values like this. So this will be the initial divinity values. And what we will do is we will decrease the divinity values from the back, right? Until the total divinity equals m. So decrease divinity until the sum of divinities is m, okay? Decrease divinity from back until sum of divinity is m. And we can always decrease the divinity. We saw this earlier. We can always decrease divinity to any number less than equal to current number, current divinity till 1. Obviously, we cannot reduce less than 1 because there's no 0 or anything in the graph. So divinity can be reduced till 1. So basically, until the sum is equal to m, we will go from the back, right? We'll go from the back and we'll find out how much to remove. So how much to remove will be simply sum minus m, right? So the current sum, which is n times n plus 1 by 2 minus m. So we'll remove from this, we'll remove from this, we'll remove from this until we finally stop and the divinity is correct. And then basically we can construct the graph. So once this is, let's say, the last point where we removed something, right? So then this will become the root node. So this becomes the root, which is the max element, right? Max element will be the root. All the elements before will simply point to the root, right? So all the elements before will point to the root, and the remaining elements will point to the value which they have been reduced to. Let's say this was reduced to 1, 1, 2. This remains 2, and remains 1. So whatever value of divinity we want, we can make it point to that to give it that value. So we can have something like this, right? So we can print the edges this way. We can say root is the max element. We can simply print that. Elements before the root, elements before root can point to the root, point directly to the root. And elements after the root, which were reduced, right? Elements after the root can point to the current value of that element. Like if the last element was reduced to 1, that means its parent was 1, right? Or if the last element was 2, then its parent was 2, and so on. So can point to their value. Okay. So first we like write 1, 2, 3, 4, n in an array. So this is the initial divinity values for the max case. We decrease the divinity from the back until the sum of the divinity array equals m, right? And then we can construct the tree by writing the root. Root will simply be the max element or the point where we stopped and did not decrease any divinity, right? All the elements before that will simply become the root's children. And the elements after that will point to whichever element gives them that value for the correct divinity. Is this clear? Why will we always connect the nodes to node 1 while decrementing? No, we will not always connect nodes to node 1. But the thing is, we'll decrement as much as possible. Okay. So we'll decrement as much as possible. So let's say right now 1, 2, 3, 4, 5 is our divinity values. And we want m equals, let's say we wanted m equals 12. Okay. So now the total sum currently is m equals 15. So we need to reduce 3, right? So from the back, we will reduce 3. We'll reduce 3. And the new value over here will be 2. So it will not point to 1. It will point to 2. Okay. But let's say we had to reduce to 10, right? So m equals 10. So then we need to reduce. So total will be 15 minus 10. So we need to reduce total 5 values, right? So here we can reduce 4. We can make it equal to 1. So then how much we need to remain? We can, if we connect this to 1, the divinity will become 1 over here, right? So currently the sum of divinities is 11. So again, we connect here. So next we can connect to 3 to reduce it by 1, right? So then the divinities become 1, 2, 3, 3, 1, right? So basically we're connecting this to 1 and this to 3. And that way the total divinity is reducing by 4 and 1 over here, correct? Does that make sense? Like we're trying to reduce the divinity as much as possible, right? So at most we can reduce till 1. So if it's going till 1, we'll reduce till 1. Otherwise, we'll stop halfway. Like here, we have to reduce only 1 more. So we'll make this into 3 and we'll stop. Does that make sense, Pulkit? Like this becomes 3. This will point to 3. Our target is m equals 10. So first we'll connect 5 to 1. Now m equals 11. We have not reached our target. We need to do one more decrease. So we'll go to 4. We'll connect it to 3. And then m will become equal to 10, which is our target. Got it. Yeah. So that's basically what we're doing. Let's first discuss the time complexity. So the time complexity for this. Yeah, if I have current divinity as alpha, I want to reduce it to m. Yeah, you'll reduce it as much as possible at the current step. And as much as possible means either till 1 or till the m value is fixed. So the time complexity for this will simply be O of n, right? So we're going backwards and we're reducing divinities until the m value is fixed, right? And then to print the tree is again just O of n, because we just need to go for each and check if we need to print it or not. So this is the way I implemented it. Let us have a quick look at the implementation. I took n and m as input, right? If m is less than n or m is greater than this max value which we discussed, we print -1. Otherwise, I made an array for the divinities. So this is my values array. Each value is equal to I plus 1. So this array equals 1, 2, 3, 4, 5, like that, right? Then remaining is how much I want to remove, right? Or remove is how much is left to remove. So that's the max minus m, right? So this much I need to remove from my array. So I can go from the back from n minus 1 to 0. If how much I need to remove is less than vals of I minus 1. So I can directly make remove equals 0 and subtract that from vals of I. Otherwise, I can say that from the remaining, I subtract vals of I minus 1 and I make vals of I equals to 1. If remaining becomes less than 0 or becomes equal to 0, I can break. Does that make sense? I'm basically doing this process itself. I'm going from the back. I'm reducing it as much as possible. If it becomes 1, then I can't reduce any further, so I'll go to the next step. Otherwise, if it does not become 1, like if it stops, like I don't need to reduce anymore, I can only reduce it to 3 or something and leave it. So I'll set that value. I'll set remaining equals 0, and then I can break out of the loop. What is Harish saying? Like I was thinking. reduce it to m. Yeah, so initially we're starting with maximum possible divinity and we're reducing it until the divinity equals m. So I'm not sure if I'm getting your question correctly. Can you like reword it? Because I'm not 100% sure what you're asking. Okay. So then we have found the divinity values for each node. Okay. At this point, we found the divinity values for each node. Now all we need to do is construct the tree. So we can write that root will simply be the max element, right? So that's what I'm doing. Root will be the max element. I print the root, right? Then for all the values, so all the values before the root, right? So all the values before the root. So here in this case, root would be 3. In this m equals 10 case, root would be 3, right? Since 1, 2, 3, 3, 1 is the final divinity array. So this is going to be the root. So all the values here will simply be 1, 2, 3. So I use that pattern. So if the value is I plus 1 itself, that means it's still in this starting phase, right? So I simply print a connection between I plus 1 and root. Obviously, if I plus 1 is the root itself, I don't need to print anything. I don't need to print an edge from root to root. So I continue in that case. Otherwise, I print a connection from node I plus 1 to the value it wants, right? So if this wants a value of 3, I can write this. And if this wants a value of 1, I connect it to node 1. And in that way, I've printed the graph, right? And that's all. You can observe that this is also big O of n, since the loop only visits the array once and calculates all the divinity values. This is also big O of n, since for each, we're just printing the edges for each node, and there are n minus 1 edges. So the whole complexity is big O of n, right? Yeah, this question was 1200. To be honest, because there's graphs, you could say that it's slightly harder than 1200. But I suppose you could say, okay, 1200, I guess. Like the idea was kind of easy enough. You did get 5,000 solves. But personally, I would put like 1300, 1400 on this. Because just because there's graphs, right? To think in terms of graphs takes like slightly higher ratings. I would say it is 1300, 1400 maybe. Okay. Should we move on to D if there's no doubts? From D, the questions start to get a bit harder. Okay. To be honest, from D, like C, I liked. As a question, I think C was nice. B was okay. I think B was not very well worded. A, I did not like at all. C, D, E were fine, I think. Okay. Problem D. Aryan and Harshit play a game. They both start with integers A, B, and K. Aryan gives Harshit two integers N and M. Then Harshit gives Aryan a matrix X with N rows and M columns, such that elements of X are between 1 and K. After that, Aryan wins if he can find submatrix Y of X with A rows and B columns, such that all elements of Y are equal. Okay. So Aryan gives you the values of A, B, and K. He asks you to find the lexicographically minimum tuple that he should give to Harshit, such that Aryan always wins. Help Aryan win the game. Assume Harshit plays optimally. The values of N and M can be large, so output them modulo 10th power 9 plus 7, right? And a tuple is said to be lexicographically smaller than, yeah, that's the normal value of how one tuple is smaller. So first we compare the first value and then we compare the second value. Okay. Let us try and understand the question. Right. Okay, so this is a bit of slightly more like very intuition based problem, I would say. Like it uses pigeonhole principle. So if you're good with that, you would get the intuition faster. Okay, so basically what it's saying is we need to give a lexicographically minimum tuple such that always we can find a into B submatrix We need to give the lexicographically minimum n and m tuple such that any matrix of n and m where all the values are between 1 and k, right? So all values of the matrix are between 1 and k, right? Then any a into b, like any of those matrices will always have a into b submatrix such that all values are equal. So this is basically what we need to find. And already you should see a bit of intuition that pigeonhole principle might be used here somewhere, right? But let's go on. Let's understand the sample. If you observe in this 3 into 3 matrix, we need to find a 2 into 2. So A equals 2, B equals 2. We need to find a 2 into 2 submatrix such that all the values are equal. Well, that is simple. We can just take this, and this, and all the values will become equal, right? That makes sense? Okay. So basically, we need to find out what is the smallest n and m that this will always hold, given the value of A, B, and K. Okay, so we are given as value. Input is A, B, and K. Right. And also let us see the time complexity, expected time complexity. So we can see that A, B, and K are 10 to the power 5, right? And some of them also does not exceed 10 to the power 5. So basically, O of A, or maybe O of A log A, O of K, O of something like max A, B, all of these types of time complexities will pass, right? Since all of them are less than equal to 10 to the power 5. So this is our expected time complexity, something like in the order of A, B, or K, in the order of n log n on A, B, and K, like A log A, B log A, K log A, something like that, right? Okay. Yeah. Okay. Boombox, you're correct. N is equal to A minus 1 times K plus 1. And yeah, let us see how that happens. So what we are going to see first is this test case 222. Okay. So we'll see the test case 222. And when we see how that test case is solved, we will get our full answer as well. So our test case is 222. Okay. So A equals 2, B equals 2, K equals 2. Okay. And with this, I will show you how you can show all answers solve. And we can see that the answer is n equals 3, m equals 7, right? And how will we calculate this? So first we need the smallest value of n, correct? So our matrix needs to be a 2 into 2 matrix, right? Our matrix needs to be a 2 into 2 matrix. And either our answer matrix will be 1, 1, 1, 1, or it will be 2, 2, 2, 2. So all the values which are in the submatrix will be equal. And they will all be equal to either 1 or 2 because K is up to 2, right? So the values of the matrix can be 1 or 2. Okay, so how do we construct a matrix for this, which is 3 by 7, and we always get the answer? Well, if you observe, if n is equal to 2 itself, right, n equals to 2 itself, then we can always write 1, 2, 1, 2, 2, 1, 1, 2, 2, 1, like this till infinity. And we will never be able to form a matrix because to form a matrix, at least two ones should be present, right? At least two ones should be present. But in each column, there is 1 and 2, 1 and 2, 1 and 2. So we will never be able to form a matrix, right? So we know that at least n should be 3. So we get n is greater than equal to 3. And since we want the smallest tuple, so n's values become fixed, n values becomes 3, right? We will make a general case for this later. But first, let us know that n value must be greater than equal to 3 by this logic. Like we need 2, 2, 1 or 1, 1, 2, something like that. We need two values to be equal in along a column. Otherwise, it won't be possible, right? To make a 2 into 2 matrix. Okay. So let's say we have 2 to 1. Now let's see how much will be the possible size of m and why m becomes 7. Okay. So now the way the matrix works is if at some other point I find another 2, 2, right? Like this column has two 2's at this position, this position. And if I ever find another 2, 2, here is another 2, 2, then I can take these four and form a matrix, right? So I'll try to delay this as much as possible, right? So I first put 2, 2, 1. Then let's say I put 1, 1, 2. Okay. Now what can I put next? Now again, I can't put 1, 1 because if I put a 1, 1, this will form a valid matrix. So that is gone for me. So let's say I put 2, 1, 1. Okay, so this is another column and I put 2, 1, 1. Now I can't put 1, 1 here again. So let's say I put 2, 2, 1. Okay. What else options are remaining for me? Now I can't have 2, 2 here and I can't have 2, 2 here, right? So let's say I decide to put 2, 1, 2 like this. Okay. So what we're trying to do is we're trying to delay the formation of a valid matrix as much as possible. Like let's say if we put 1, 1, 1 over here, this will simply form a matrix like this, right? So sorry, like if I put 1, 1, 1 over here, these two, I can take these out and form a submatrix where all the values are equal. And submatrix size is 2 into 2. So I'm trying to delay this as much as possible, right? So if there's a 1, 1, I'm trying to not put a 1, 1 again. Similarly, 2, 2, I'm not trying to put a 2, 2 again. Similarly, this 1, 1, I'm not trying to put. This 2, 2, I'm not trying to put. Well, the only option remaining now is to put this, right? Since there was no 1, 1 ever before at these positions, then this will also not form a matrix. But now no matter what I put in the next step, so you can see that this is 3 and this has become 6, right? Now no matter what I put at my 7th step, always a submatrix becomes formed, and I'll show you how. So let's say at my 7th position, let's say I put 2, 1, 1. Okay, then this matches this column, right? And basically what happens is this form a submatrix, right? Otherwise, if I like, let's say I put 2, 2 here, right? Then this will match here. Sorry, this will match this. This will match this, right? So again, I got a 2 into 2 submatrix with all my values equal. And since, let's say I put all 1, 1, 1, then this will match here, right? So basically, I'm seeing that because all the possible positions for two values have been covered. Basically, all positions for all arrangements for 3 choose 2 times how many colors I have? 2 colors, right? Have already been taken. I'm not able to find a new can't make any more basically. So I can't increase this any further, right? Like all these positions have been taken. So I'm not able to add any new colors because it's going to conflict with something or the other, right? So this is our key intuition for the problem. It's a very pigeonhole principle idea. So key intuition is that basically at some point I'll reach a point such that if I add this color, any color which is occurring more than um, a certain number of times, it's going to clash with some numbers in the previous array. So basically, how do we write this down in a general case? Let us figure it out. So first, let us write the general case for n. And we can show that the general case for n will simply be a minus 1 times number of colors plus 1. And how can we show that? We can show that with pigeonhole principle. We can say that the first color appears a minus 1 times. Okay. So there are, let's say, k colors, right? So let's say there are 5 colors or first number or whatever you want to call it. I'm calling it colors just to make it simple for myself. Like I'm assuming that it's like a grid and we're coloring it. So these are the numbers we're putting in the matrix. And so if we make a matrix and let's say let's say A is 3, okay. So then I can put 1 twice, 2 twice, this thing twice, this thing twice, and this thing twice, right? And if I always make every column like this, then I will never be able to form a matrix because my matrix needs a side of 3 and I will never get a side of 3, correct? So that's why if I put one more, by pigeonhole principle, one of them must have 3 elements, right? By pigeonhole principle, one of them must have 3 elements if I put one more. Let's say if I put 3 over here. So then I get this, and I can use it to form my matrix, right? So I can use it to form my matrix because this has become A, right? So basically, we're doing pigeonhole principle until one element is A, and that is going to be our value of n. Okay. So we can write our value of n as n equals a minus 1 times k plus 1, right? So basically, I'm doing a pigeonhole principle. I'm assuming that I'll fill the colors until they're a minus 1, and I'll fill the numbers until they're a minus 1. And in the end, I need to fill one more to make sure at least a numbers are the same along a column. So by pigeonhole principle, to make sure at least a numbers, make sure that we can find a numbers which are the same along the column, right? So we need to find a numbers which are same along the column. So by pigeonhole principle, since there are k different values of numbers, the answer for n is n equals a minus 1 times k plus 1. Okay. So now that I have my n, right? I have my n. I need to calculate my value of m, right? I need to calculate how much m it is until I get some a colors over here and a colors at some other point, right? Which are all equal, right? And if and I can get b of these, correct? I can get b of these. Like I need a, and all of them same color. And I need b of these. Like let's say b was 3, then I will need 3 occurrences of this, right? So this again we will do by pigeonhole principle itself. So the number of ways to arrange the colors. So if we assume that how many colors are there? There are k colors, right? So the number of ways to arrange the colors, these a colors, will be simply n choose a. So n choose a is the number of ways to arrange these a colors in one column. And because they are k colors, we can have this configuration appear k different times, right? So for example, in the above case, we had n equals to n equals 3, right? And a equals 2. So this would become n choose 1, or it will become 3 choose 2 times k. So basically, what I'm saying is like we have 2 2 over here, right? Now a different arrangement is 2 2 over here, and then a different arrangement is 2 2 over here. Similarly, we can have 1 1 over here, we can have 1 1 over here, and a 1 1 over here. And these are all the different possible arrangements of 2 2 1 1 I can do until some new arrangement starts clashing, right? So I can either have 1 1, and then this can be any value, and then I can have 1 1, and this can be any value. Or I can have 1 1, and this can be any value. Then I can have 2 2, and this can be any value. 2 2, and this can be any value. 2, this can be any value, and 2. And then any new arrangement I put, something will clash, right? So basically, one of the arrangements will clash with one of the colors. And now we want B clashes total, right? We want B clashes since the width of the submatrix is B, right? So we want this thing to occur B times. So we can simply multiply by B and add a 1. So as soon as we have this many, if we add one more, it will clash. By pigeonhole principle, it will clash with B others such that we have B columns such that the same arrangement of the color K, whichever color it is, let's say the color is 1 itself, right? So the color 1 itself appears in this particular arrangement of n choose A, and it appears like this B times, right? So as soon as we add one more row, it's a very similar pigeonhole principle to how we calculated n equals A minus 1 times K, except it's slightly more complicated. So basically, n choose A is the number of arrangements of a given color, K is number of colors. So it's like that same thing we did over here. 1 1 1 1 1 1 like this. And yeah. Oh, and it should occur B minus 1 times. Sorry. Is B minus 1? because once b minus 1 is done, the next one will clash with something or the other, right? For the same reason, this was a minus 1 over here. The same reason this was a minus 1. This will be b minus 1. Because once this, all the colors have repeated b minus 1 times, as soon as we add one more column, all the colors in all the arrangements have repeated b minus 1 times. As soon as we add one more column, our pigeonhole principle will be satisfied, and there'll be at least b colors and b arrangements of some color which are matching at least b times. Does that make sense? So this is the formula for n and m. So we can write n as a minus 1 times k plus 1, and m we can write as n choose a. So that is the number of arrangements of color, some specific color which occurs a times. There are k different colors, so we can repeat those arrangements that many times. And then we need b minus 1 because we need this clashing to occur b minus 1 times. And as soon as one more clash occurs, we know that we can form our required submatrix of size b into a. Okay, so this is the two formulas. And then all we need to do is implement this in code and we get AC. All right. Have they declared it unrated? I'm not sure. I need to check, I guess. If they have, then they must have put an announcement, right? Well, we'll come back to that. Let us just finish off this question. So then everything in this is fine. You can observe that the value of n, because k and a goes up to 10 power 5, this will be something like 10 power 10. So it fits in long, right? This obviously will not fit in long, since n choose a will become very large. N is like 10 to the 5. N goes up to, sorry, 10 to the 10. And then choose a. A also can go up to 10 to the 5. So this can become very big. But the way we will do it is we'll use modular arithmetic to calculate it. Use mod arithmetic, right? You would know how to calculate n choose a. The way we do it, like we can write n choose a something like this, right? We can write it as n times n minus 1 times n minus 2, like this, right? N choose a, we can write till n minus a plus 1, right? And then it will be something like 1, 2, 3, so on until a, right? So we will calculate this value using modular arithmetic, right? So you will need to do modulo division, right? So we will calculate this product using modulo operations. So you need to know how to do like modulo division, mod multiplication and division. So then we can calculate the value of n choose a. So I just have a template for this directly, like to do modulo division and modulo this thing. You can just Google it if you don't know. And then we can just calculate this whole value, okay? And this was a very formula-based question. I don't see it being unrated yet. It hasn't been mentioned in the official blog, at least. So the unrated announcement has not come yet, at least. I'm not sure if they'll unrate it or not. Like previously also, there were some bad rounds. Like if you had done Goodbye 2024, I think, sorry, Goodbye 2023, it was a pretty bad round, but they never unrated it. Okay, so let's just have a quick look at how to code this. So this is just for modulo operations. If you don't know how to do modulo operations like add, subtract, multiply, modulo exponentiation, and inverse regarding some modulos, it is used for finding modulo division and stuff like that. So just Google it. It will be there on CP algorithms or something like that. Also, if you're doing TLE course, it should be there in level 3 or level 4, I suppose. So definitely do check it out, how to do modulo operations. Anyways, so n we use directly that formula, a minus 1 times k plus 1. And we calculate the value of m. M is n choose a times k times b minus 1 plus 1. So we set m equals 1. We do that multiplication, right? So here top and bottom represent this n and 1, right? They represent n and 1. And we multiply n to the top, divide by 1, then multiply n minus 1, divide by 2, multiply n minus 2, divide by 3. That's what this loop is doing, right? Until the bottom equals a. Top is n, bottom is 1. We subtract by top, increase by bottom. We multiply by top and divide by the bottom, right? So to divide by bottom is simply multiply with the inverse of the bottom. Then finally, we finish the formula. So once we have found n choose a, we multiply it with k and we multiply it with b minus 1. We add 1 and we print the answer. And now be careful to print n percentage mod, otherwise the answer will be incorrect, right? Because here we did not take n percentage mod to do this whole calculation. And n percentage mod fits in long long. Like n itself fits in long long. So we took the mod at the last step and we printed. Meanwhile, for m, we were taking mod at each step using our functions, modular functions here. Okay, so that's about it for D. Any doubts, please ask. Otherwise, within a minute, we'll move to E. Okay. Should we move on to E, guys? And there was a decent amount of cheating this round. I think seeing the standings, there seem to be so many pupils at the top. But I'm not sure how much more it is than a usual round. Because like nowadays, GPT solves, I think, up to maybe D or E, it would easily solve. And maybe with some, like maybe if you have GPT Premium, you might be able to solve more also. So I don't know. Like cheaters are always there. I don't think IIT KGP might have made some specific mistake because usually the authors are very experienced, right? Anyways, problem E. Let's quickly finish it up because it's getting late now. Lanes of cars. This was a bit of a complicated problem, so it might take some time. E. Also for the above, the time complexity is big O. The final time complexity is big O of A per test case. Since for N, it's simply a formula. And to find N choose A, we see that it takes A steps. So the time complexity is big O of A per test case. Okay, for D. Now for E, okay, let's read the question quick. Harshit is the president of Toll Club. He asks his subordinate to oversee a toll plaza with N lanes. Initially, the ith lane has A of I cars waiting in a queue. Exactly one car from each of the lane passes the toll every second. The angriness of a car is defined as the number of seconds it had to wait before passing through the toll. Okay, so the number of seconds it has to wait to pass through the toll. It takes 1 second for each car to pass through the toll. So the first car has angriness 1, second car has angriness 2, and so on. To reduce congestion and frustration, cars are allowed to switch lanes. A car can instantly move to the back of another lane at any time. However, changing lanes increases its angriness by an additional k units due to the confusion caused by the lane change. Okay, so we can move the car to any lane, but it will add another k units to the angriness. Harshit wants to help drivers by minimizing the total angriness of all the cars. He asks Aryan to do so or get fired. Okay. So we basically need to minimize the angriness using this operation. Okay. So we're given as input n and k, and we are given an array A, and we need to minimize the angriness. So basically, what is the question asking? It's saying, let us draw the lanes. Okay. So let's say for this question, there are 3 lanes. So n equals 3, and there are 3 lanes. And there are 13 cars in this lane, 7 cars in this lane, and 4 cars in this lane, and k equals 4. So basically to remove one car from, let's say this lane and put it here, right? That gives us a cost of 4, right? So every time we move a car, it's going to give us a cost of 4. So for example, this will become 12 and this will become 5. And the cost of this movement will be 4. And finally, what is the angriness of all the lanes in the end? Once we have finished moving everything, the angulars of this lane will be something like 1 plus 2 plus 3 plus till 12, right? Similarly, the angriness of this lane. So each car in this lane will have the angriness equal to the distance from this, the time it took to get out of the lane, right? So the final angriness will be something like this, right? So basically in the start, we rearrange the cars using this value of k, which increases the angriness. And then when they get out, um, when they finally go out, their angriness will be how much time it took them to go out. So it'll be simply like for each lane, it will be a of I times a of I plus 1 by 2, right? So for each lane, it will become a of I times a of I plus 1 by 2. That's how much it is going to become for each lane. And we have to basically minimize this value. And plus, let's say X number of lane changes we made. So this plus the sum of these, plus if we made X lane changes, X times K, right? So that's basically what our question is asking. Did they make it unrated? Not yet, I think. It's a bad contest, yeah, I would say. Like A, B definitely were not that nice. Anyways, B was too much geometry. A was again too much geometry, and there were too many cases in A, I would say. But yeah. Okay. So what is our key intuition here? Okay. So since it's getting late, I'll try to hurry up the solution, right? So key intuition here is we have 12 cars over here, right? Let me just write it like this. So we have 12 cars over here, and their costs will be like this. Like the angriness will be till 12, right? Similarly, the angriness of these cars, I'm writing down, okay? And the angriness of these cars, I'm writing down. Now, if we want to add any car to the back of this 3, right? What will be the new angriness value? Well, this new car, let's say this new car which I added at this position 3, right? Now it will have an angriness of 4 because it needs to get out over here, right? Plus K. Correct. The angriness will become 4 plus K. So if I want to add a new car, and this is, I will put in orange because there is no car over here yet. It is just to see if I want to add a new car, then the angriness will become 4 plus K. Similarly here, if I want to add another car, it will become 5 plus K, 6 plus K, 7 plus K, and so on, right? Similarly here, the angleness will be 8 plus K if I add a new car to this line, right? 9 plus K if I add a new car to this line, and so on. Here it'll be 13 plus K if I want to add a new car to this line, and so on, right? Right, does that make sense? Yeah, so this is basically the cost of how many of adding a car behind some already given line, right? So in the first line, the cost of the first 12 cars will simply be 1, 2, 3, 4 till 12. The angriness, let me just use the word angriness and cost interchangeably because it's coming out as that. Anyways, and then in the second one, the angriness goes from 1 to 7. And then after that, if I add any extra cars, the angriness will become 8 plus K for that car, like effective angriness. Similarly, for 3, I have 1 to 3. And then if I add any new car, it's like I added K and then I added 4, right? So effective angriness I'm adding is 4 plus K, then 5 plus K, then 6 plus. Okay. So now what I'm going to do basically is I'm going to do a binary search. Okay. So I'm going to do a binary search. So these are our values of effective angriness of a car. So let's say if I added only some cars, first 6 over here, first 6 over here, and first 6 over here, right? So then this much, and this much values will be added. And basically, if I can somehow, instead of taking this as my sum, if I can somehow take my sum, something like this, right? If maybe this sum is a good sum, like lesser sum than the previous one, or I can take, let's say, something like this, right? So if I can be able to move my cars around such that I choose some elements from this, some elements from this, and some elements from this, such that the number of elements total is equal to the original 12 plus 7 plus 3, then I can find a valid solution, right? So I need to find the minimum solution to do this. Okay. So what I'm going to do is if you think a bit on this, like I thought many approaches in the start. I thought first a normal binary search on the answer, but that was not working. And then I had some ideas like use a priority queue, and maybe there is some solution using priority queues, but I was not able to think of it. Then I thought about this solution, like using this effective angriness idea that any new car has this additional effective angriness. I'll say that I'll pick all the cars. I'll pick all the cars with with effective angriness less than equal to some x. Okay, so I'll pick all the cars with effective angriness less than equal to some x. Okay, so let's say if I choose x equals 4, that means I pick the cars this, this, and what is value of k? So for this example, the value of k was how much? The value of k was 4, right? So 4 for 4 becomes 8, right? So this becomes 8, 9, 10, so on. So therefore, I'll pick this, and this, right? Otherwise, if I say effective angle is up to 8, I'll pick. That means I can pick this, and this, right? So if my effective agonist was up to 8, I can pick these cars. So basically, I will pick all the cars with effective angularness less than equal to x, and I will check if numbers of cars I could pick, if number of cars I could pick is greater than equal to sum of all AI. And why is that? Well, I know that my total cars will be 12 plus 7 plus 3, right? So that is 15 plus how much? That's 15 plus 7. So that's 23, right? No, wait, not 23. 22, right? So I need to pick total 22 cars. So if I choose effective angriness as 8 as my maximum, right? Then I get 8 from here, 7 from here, and 4 from here. So I can say that there's not enough cars to rearrange in such a way. Then I can say that, okay, I take effective angriness of, let's say 10, right? And then I get some more cars to pick like this, maybe, right? If I take effective angriness up to 10, and then if I have enough cars, I can know that I know that this is a valid maximum value of effective angriness. And then basically, I will check if number of cars I could pick is greater than or equal to sum I. If it is, then this is a valid value of maximum effective angriness, right? This is valid value of what I call maximum value of effective angriness, right? Otherwise we could say that it's too small. Otherwise, x is too small, and we should increase x, right? So what I'm going to do is I'm going to do binary search on the effective angriness value such that we can pick all the total number of cars which we want. Okay. So binary search on max value of effective angriness. Okay. So let me define one thing. Let me define a value sum equals total number of cars equals sum of all values of AI. Okay. So basically what I'm saying is binary search on T such that if I choose all cars such that my effective angleness is less than equal to T, then even so, like if let's say there are X cars such that the effective angleness is less than equal to T, or let's say count cars, okay, then this count should be greater than equal to sum, right? This count should be greater than equal to sum for this to be a valid maximum value of effective angleness. Then with binary search, I'll find the minimum value of T. So minimum value of my effective angleness. Minimum value of T, which is the minimum value of my effective angleness, such that I can make it. So that means that basically only taking all cars with less than T effective angleness, T minus 1, doesn't take enough cars, if I take only up to effective awareness t minus 1 and t takes greater than equal to some cars. Okay, so it's going to be my key idea. I'm going to do a binary search for my effective angriness such that I can take all my cars, and I'm going to find the minimum value of effective angriness I need to take so that I can still take all the cars present. Okay, so what did we do? First, we showed that to add any car at the back, let's say at the third, at over here, if we add any car at the back, then effectively to add a new car, the effective angriness is like 4 plus k, 5 plus k, 6 plus k, and so on. And then I'm trying to binary search. So what is the maximum value of effective angriness I'll take? And that way I'll find the minimum value of max effective angriness. And based on that, what I need to do is take all cars with effective angriness less than or equal to t minus 1, right? And then let's say we took CNT cars, count, CNT means count, okay? So let's say we took CNT cars. There are CNT cars less than this. Now we need to take remaining sum minus CNT cars at effective angriness of t, right? So let's say the cost for taking, or the sum of effective angriness over here, let's say that is sum, or let's say that is ans. Okay, let's say that's our answer. Then our final answer will simply be that answer plus sum minus count times t. Okay, where t is the value we binary searched, right? T is the minimum value of effective angriness such that we can still take all the cars, right? Does that make sense, guys? This Codeforces down. Yeah, looks like Codeforces is down also now. I'm also getting 404 not found. Maybe they have some server issue or they're trying to fix something. So this is a E problem, so maybe it might be hard to understand. But basically what I'm doing is I'm trying to binary search on how many I need to take from my first lane, second lane, third lane by restricting the maximum effective angriness I will take from any lane. Then I'm saying I'll take everything in my lane such that my effective angriness is less than my current binary search value. And then I'll find the minimum effective angriness to take. And then based on that, I'll find my final answer by taking everything with effective angriness less than this. And the remaining I will fill with effective angriness of t. So what will the binary search look like? How to binary search? Search t. Okay. So let's say my L is, let's say L I can set as 0. So obviously L should be 1 because at least one car is there. But see, let me assume my effective angriness is 0. Okay. And my R value of R is, so what is the maximum value of effective angriness I need to take? And we can show that that is equal to sum plus M or sum plus K. Wait, what does the question say, M or K? The question says K, I guess, right? So it will be sum plus K, right? So this is the maximum value of effective angriness we can ever take because that means it is behind all the cars, right? It is behind all the cars and it occurred an additional cost of K. And that is the maximum value of effective angriness for any car that we can take, okay? So from L equals 0, R equals sum plus K, we'll do binary search. So we'll do while L less than equal to R, so normal binary search. Mid will be L plus R by 2. Obviously, you should write this so that it does not overflow, right? L plus R might become big. Then what we're going to check is if we'll try to count all cars we can take in each lane such that it is less than or equal to mid in effective angriness. Now we get a value count, right? So now if count is greater than equal to sum, that means it is a valid value. So we can update our binary search, update binary search value t to be equal to mid. So t is our final answer. And we can say that r can become smaller. So r can become mid minus 1. So now we need to search on the left half. Otherwise, this was not enough. So we must search on the right half. And this is how we can write our binary search. All right. And how do we count? How do we do this part? How do we do this part? Count all cars such that they're less than equal to mid. Count all cars with effective angriness less than equal to mid. We can do this in big O of n, and I'll show you how. So for each lane, right? So each lane, let's say we had that lane 1, 2, 3, 4, and then after this it is 5 plus k, 6 plus k, and so on. Effective value we have 7 plus k, right? So for each lane, so obviously if our effective value is mid, right? So if a of I is less than or equal to mid, right? So if a of I is less than or equal to mid, that means this, or let's say if a of I is less than or equal to mid, then what does that mean? It means that we can take all these cars and we might need to take some cars more from here, right? And what if a of I is less than or equal to mid plus k? Okay. Right. So basically we need to count how many cars here mid are less than or equal to mid, right? So we can say that if a of I, let's do it the other way around so it's easier to understand. We can say that if a of I is greater than mid, right, or greater than or equal to mid, then we can simply take mid cars, right? Otherwise, if mid is greater than or equal to a of I, but less than or equal to a of I plus k, right, then we can simply take a of I cars, right? And then otherwise, so our count becomes plus equal to mid over here, and our count becomes plus equal to a of I over here. Here we're counting how many cars we can take less than the given cost, right? So here our count becomes plus equal to AFI. And otherwise, if mid is greater than equal to AFI plus K, then we took the first AFI cars. So we add AFI, right? And then how many other cars we're taking? We are taking, so from this point onward, let's say our max was, let's say, 9 and our K is 3, right? So we can take these two basically, right? So how do we figure that out? We can simply say, so we took our initial AFI, and then after this, we can take up to 6 basically, right? Because we can take up to mid minus K, right? So we can take up to mid minus K. So let's say our mid was 9, right? This is up to our effective value. K is 3. So that means basically this is 5 plus 3, 8, 9. So we can take these two additional cars if our effective value goes up to 9, right? So we can count these two. So basically 9 minus 3 is 6. So we take mid minus K, and these are the total number of cars we can take. So in this case, we can simply increase our count by mid minus K. So these are just some cases you need to be careful while writing them, right? So this is case 1, this is case 2, and this is case 3. Okay. So in the first case, if AFI is greater than mid, then we can simply take all mid cars up to mid. Otherwise, if AFI plus K is greater than equal to mid, is greater than equal to AFI, so that means mid stops here. So we took all the first AFI cars. Otherwise, we can take mid minus K cars up to mid minus K, total number of cars, with the given effective angriness equal to less than equal to mid. Does that make sense? right? I hope you guys are following. So we're binary searching on the minimum effective angleness required to take enough cars. So right now for a given value mid of effective angleness, we're counting how many cars to take. And then once we have done this binary search, so now once we have done binary search, once the binary search is done, now we need to add all cars with effective value less than equal to t minus 1, right? And then let's say they are CNT of these cars. Let's say their total CNT of these cars. Then our final answer will include. So we need to add the angriness of all these cars. Add angriness of all cars. So our final answer will be this. So let's call this ans plus CNT times T, right? This is going to be our final answer like we discussed earlier. We discussed it here, right? So what all did we do? We found out the effective angriness values. Like we thought of it in effective angriness values. We're binary searching for the minimum effective angreness value which we can take. We can take all the cars less than equal to this minimum effective angreness value to make sure that we took enough cars. We're doing this binary search. And now once we have found the T, minimum T, we are going to find what is the actual angreness value of our solution, right? So this is how we're going to do it. So again, we loop through all AI, loop through all A of I. Again, we have three different cases. If A of I is greater than mid, so case one is if A of I is greater than or equal to mid, right? Or not equal to mid now, T minus 1, right? If A of I is greater than or equal to T minus 1, then that is something like this, let's say, and then we had 6 plus K, 7 plus K, so on. And these are our effective values, right? So let's say our T minus 1 was something like this, right? Then we need to sum the angreness values of all of this, right? So we can write our sum as answer plus equal to T minus 1 times T by 2. Because we're summing 1 plus 2 plus 3 plus 4, everything less than my current angriness, right? Now what if our effectiveness value was somewhere in between? What if T was over here, right? Less than this and greater than this? Then this is our second case. So here we're finally counting the final answer, right? So here, if our T minus 1 is greater than or equal to AI, but it's less than or equal to AI plus K, right? So in this case, we simply sum the first AI elements, right? So AI times AI plus 1 by 2, right? So we're simply finding, for example, for this, we're finding 5 times 4 by 2, which is the sum of the first 5 elements, right? And then finally, what if T minus 1 was greater than or equal to AI plus K? Well, then we simply need to find again. Observe that we simply need to find the sum from this 1, 2, 3, 4, obviously, and the sum up to here, and then we subtract this sum, right? So again, we're subtracting and adding the same value. So basically, it's going to be, we need to find 1 plus 2 plus 3 plus 4 plus 8 plus 9. Basically, we need to find this sum in the given example. So we can find it many ways. You can write out the equation and make it simplified, right? So basically, we need to find. So if you observe the count, we can increase our answer by the first few values. So the first few values are simply uh, AI plus 1 by 2, right? And then we need to find this sum of 8, 9 as well, like till wherever it went. So how many will that be? That will simply be, count will be, let's say, T, it was T1, T minus 1 minus K minus AI, right? So these are the values which are continuing to increase over here. So 8 and 9, there are two of them. And you can see that the number of the elements will be 2 because we are not counting the first 4 elements, right? The first 4 elements we already summed. Now we're just summing this 8 and 9. So we are summing 2 elements. So basically our answer will be again plus equal to sum of all the elements. So up to 9, right? So up to 9. So how do we figure out that 9 was our largest? Well, that is simply ti minus 1, right? Minus. So some expression like this. Obviously, you can work out the exact formula and simplify it. Like in the contest also, I simplified this formula a little bit. It's already a bit late, so I'm a bit tired to simplify it right now. But roughly what we're doing is like we're adding the effectiveness values this way. The effectiveness values were like this. Effective angriness values were like this. So let's say 8, 9, 10, 11, right? So basically we're finding the sum. Let's say this was t minus 1, right? T minus 1 equals 9 at this point. So basically we're finding the sum of this. Then we're finding the whole thing's sum, right? Up to 9. We're finding the sum up to 9. And we're subtracting the sum up to 7 to get the sum of 8 and 9, right? Sum of 8 and 9 will be sum of all natural numbers till 9 minus sum of all natural numbers till 7. And then this part is simply sum of all natural numbers till 4. So that's basically what I'm writing here. I'm finding sum of all natural numbers to 4. I'm finding how many elements are here. Then I'm finding sum of all natural numbers to 9 minus sum of all natural numbers to 9 minus C and T minus 1. So S of 9 minus S of 7 is basically what's happening here. And I'm finding how much is the sum of angriness values of all the cars over here. Okay, right? So let's just have a quick look through the code. And then after this, obviously, we can use directly this formula, this answer which we obtained times count plus T, where count should be sum minus count, sorry. Right, so how many cars are remaining? That much times T, because the remaining will have effective angriness of T. Let's have a quick look at the solution. Okay. And yeah, let's talk about the time complexity. So the binary search is the main part of this. To find the final effectiveness values, it's simply one loop. So this is big O of n. So the total complexity will be, and also at a given binary search step, it's also taking big O of n to find the count. So it's going to be big O of n. So a predicate function takes big O of n times the range of binary search, right? Log of that range. And that range is log of sum of all a of I plus k, right? So this is our final time complexity for the solution. Because the maximum value R goes up to this much, okay? Now, while coding the solution, I wrote k as m, I think, because I was still thinking of the previous problem. So over there, it was n and m. So everywhere where I used k, please, while reading the code, change it to m, okay? So let's go through the code real quick and see how I implemented this. I take n and m as input. I create a vector of size n. I take in the input and I calculate the sum of all cars. So because I mentioned that we need to know the sum of all cars to know whether we took enough cars or not. Now I have L and R, where L goes from 0 to, and R goes till sum plus M, which is the maximum effective angriness. And T will be my minimum value of maximum effective angriness needed. Okay. So then I find my mid value and I wrote it this way to avoid overflow. I will count if in this given n and m car, in the given values of n, m, and the vector, whether if I only take cars which have effective angriness less than equal to mid, I have greater than equal to some cars, right? So that's what I'm trying to do. And in that case, if it's true, I can update my value of T and go search the left-hand side. Otherwise, I search the right-hand side in my binary search, right? And what does the count take function do? It checks if we can take counts how many cars we can take at an effective angriness less than or equal to k, right? So we go through all the cars. If x is less than equal to y, we just increase that in the count. Otherwise, if x is less than y plus m, we increase the count by y. Otherwise, we increase the count by x minus m. And if you observe, this is simply the three cases over here, right? This is the three cases we mentioned over here. This case, and this case. If a of I is greater than mid, then we increase the count by mid, right? So this is the first case. The second case is, sorry about that. The second case is if x was less than equal to y plus m. So the variables are different, but you can see that it's the same thing. If a of I plus k is greater than mid, so yeah, if it's between this and a of I. So obviously, if it passed the first case, it will be greater than y, right? But if it's less than y plus m, then we can simply take the first y cars, and that's our answer. Otherwise, we are taking x plus m cars, and that's the increase in count. If at any point count becomes greater than sum, I return true. Otherwise, I return false. Okay. So this is how to implement the predicate function. And this will find us t, which is the maximum effective angleness of any car which we took. Okay. So now I need to take every car of cost less than t, and the remaining, how many are untaken, they will be given effective angleness of t. And I need to sum all those values up. And I basically implement the same thing. Count is how many cars are being taken which have effective angleness less than equal to t minus 1. And answer is the sum of their anglenesses. So every time I increase count. So if you observe, the increase of count is exact same as this, right? So the increase of count is the exact same as this. And then again, I do my three cases, right? So my first case, I simply take up to the value of t. Otherwise, if t minus 1 is less than equal to x plus m, then I can simply take the first x values, the first x cars, and then otherwise I need to take a mix of both, right? I first need to take, let's say, these four, then these two, or if my effective angleness went up to 10, then I need to take these three and these four cars. So basically, I'm finding that sum. If you work out these equations, you can simplify it. Like this equation is a bit longer, although it is correct. You can simplify it to this because the subtraction and the addition cancels out later on. So just go through the code once after the PCD. Then finally, we're increasing our answer by the remaining values, which have been remaining cars, which are being given effective angleness of t, and we're printing out the final answer. Okay. So it is a slightly complicated binary search, I would say, right? It's not a very straightforward binary search, but yeah, once you start thinking in terms of effective angleness, and you start thinking in terms of how many cars should be less than equal to what value of effective angleness, it becomes pretty simple. As you can see, it passes all the samples, right? We already discussed the time complexity. It's n times log sum a of I plus k. And I showed why R is equal to sum a of I plus k, right? So sum plus m. In the code, m is k, so sum plus m, right? And so I would say fairly standardish binary search type of problem. Okay, fine. We can take general questions now since we did all the questions. Any doubts regarding any of the questions, and I can recover them, or any general questions? Let's go. You can ask me now. Okay, Codeforces seems to be down again. Nice. What is the IDE I'm using currently? It is Sublime Text. The Sublime Text, the free version. There's a free version of Sublime Text. You can set up like this input.txt, output.txt stuff, using, like if you go to preferences and stuff, like if you just Google how to set up Sublime Text for competitive programming, they'll show you how to do all this stuff, right? So yeah, you have layouts and groups. So I'm getting my input, output, and time taken. Then you can write your own build system so you can get your time taken and you can run your input output with whatever compiler you want. So yeah, you just Google how to use Sublime Text, you can get it. Although obviously it's not the best or anything like VS Code or Vim or whatever you want to use. Anything is fine. The editor does not really matter as long as it's comfortable for you. This is distressing for honest Indian coders. Yeah, that is true. Like, please guys, definitely do not cheat, right? Because nowadays it's become really easy to cheat. And the thing is, there's no point in cheating. Like, once everyone starts cheating, right, the rating won't even matter for placements or anything like that. Already, no one, not many people in placements care about rating. And then online assessments you have to give yourself anyways. So there's no point in cheating or getting an ego boost. Like what? There's no fun in copying, pasting from ChatGPT or something like that, right? So definitely don't cheat, guys. It also makes the reputation of Indian coders bad, I guess. How did you prepare for INOI? Well, to be honest, there were some Discord servers where I found friends who were also preparing at the time. So if you're like in 11th or 12th, then do check out the official INOI website. I think they link like a summer camp or summer like Discord server or trading program, something like that. So I found people over there, and then I just used like USACO materials, stuff like that. Okay. Do you think 2 years will be enough? Yes, 2 years is enough. But the thing is, like you'll have to balance other things. Like personally, I was doing JE, so I could not quite reach IOI. But yeah, if you're smart and motivated, you can definitely do it in 2 years. When will the rating be out? Not sure, probably tomorrow morning-ish. If they're going to unrate the round, which is also possible, then obviously rating won't be out ever. Any other questions, guys? And then otherwise for INY, I just did like normal CP practice and obviously do old problems, do previous year questions, whether it's INY or ICPC or whatever you're preparing for, any exam, any OA. Always it's the previous year questions which are the best source for anything, right? And obviously all these competitive programming related contests, practicing on CF, practicing on Code Chef, Lead Code every week, every trying to do every contest. That helps a lot. Upsolving the questions you don't get. So always upsolve one question more than what you got. Did they ban Codeforces? Obviously not. It's just um, the website is down probably, right? How to reach expert from specialist? First, obviously, you need to know all the basic concepts, right? So I think for becoming expert, you should definitely know all the concepts in TLE level 4 also. So any all the concepts, just go to the TLE website and refer the topics they have. Level 2, 3, level 4. Whether you want to learn from TLE or elsewhere, you can make sure that you know dynamic programming, graphs, and maybe DSU and segment tree might not be required to become expert, but it's helpful to know, right? And definitely combinatorics, binary search, all those basic concepts you need to know to become expert. And then, and obviously do practice on C and D problems, especially in Div 2. In Div 3, problems on D, E, F problems, and then eventually you'll become expert. There's no secret, you just practice. What is your opinion on today's contest? I think A and B were not nice. C, D, E were fine. Although C I found was a bit too standard. I think, I'm not sure. A and B was, I think it was too much, like A was too much geometry, too many cases, and B was again geometry, and it required like some intuition, physics intuition, which you cannot really expect, people who are coming to solve programming problems to have physics intuition. Yeah, it was conservation of momentum, or not exactly, conservation of kinetic energy, I guess. Like whatever, it's been a while since I have done physics, but yeah. If you have physics intuition, you could see that two balls are just swapping, right? And that the number of balls in the diagonals are not changing. That idea would come very fast if you had physics intuition. So I would say for a B problem, requiring physics is not that great. Like in ICPC, I understand. In ICPC, a lot of questions they give, real world style. They give physics and stuff, and it's expected over there. In a Codeforces B, it's not really expected. And the question wasn't phrased easily in such a way that, people who don't know physics People who don't know physics would be able to understand just by reading the question. DI solved till the row, but the column is hard. Yeah, that's true. The row pigeonhole was quite easy, but to find the column was a bit harder. But then the logic was the exact same logic, just extended a little bit more. So if you could do the row idea, then the column idea should not be that much harder. You just need to think about it, meditate on it a little bit, and then later when you see a question like this, you might be able to do it next time. Like we used the exact same pigeonhole idea, except we saw how many arrangements of each color was valid, and we made sure that b minus 1 columns are there. So as soon as we add a new column, it will be valid. Okay. Yeah, column was the main problem actually. Like row was simple enough to get. But to be honest, as soon as I got row, I got the column also within 4 or 5 minutes after that. Like same idea was applied again. Any other questions? It's almost 12. It's almost 1 in the night, so we'll end the stream soon now. I'll just wait a minute if anyone has any other questions, or we'll end the stream. Is there a high chance the contest will be unrated? I can't say. Like, I need to go read the blogs and see what people's opinions are. I'd say it's a 50-50. Like, I feel like this contest was made by less experienced setters, so they might decide to unrate it. 50-50 a chance, I say. Not sure, actually. I can't really tell. There was a lot of CF issues also. Like, CF was taking too long to load during the contest for me. No, I can't personally review your code right now, but if you are a TLE student, definitely you can make a new doubt, and either me or some other high-rated mentor will see your code, and you can ask them for tips maybe. If you are in the TLE self-paced course or any TLE course, and you have access to doubt support. All right, then we'll end the stream now. Again, a reminder, TLE self-paced courses are out now, and they're at a discount, so do go check them out, right? If you get stuck in contests and stuff. So if you're feeling like you're stuck and you need an ordered and structured way to continue, definitely do check out the course. And that's about it. Thank you very much, and see you all next time.